Hello everyone, thank you for being here in my talk, Coding and Bounds for Partially Defect Memory Cell. This joint work with Sven Poshinga and Antonia Wachter-Zeh from Technical University and München. The initiated idea introduced by one in 1974 and then further studied in two, considering error as well, and then further asymptotic analysis and further study in 3 and 4. And recently, in 2016, partially stuck cell scenario presented by Antonia and Eitan Yakubi. And this is our references here. Full version of the paper. So this work partially summarize our construction and bounds in 6 and 7. So the paper from the Redundancy 2019 in the Moscow conference, and the 7 in the ACCT 2020 published soon, will be published soon in IEEE, and it's in Bulgaria. So the motivation for a code for non-volatile memory, actually a non-volatile memory is a memory that stores the information even when power off. For example, multi-level flash memories. So the electronic charge represent multi-levels. If charge is trapped, a level can only be increased, and cell can be stuck, cannot change their values, and rising block. So if we could, for example, rising the whole block and write on the memory again, but this will slow and decrease the lifespan of the memory. So to avoid by increasing level in a new write. So for the stack position or partial stack position, we just increase the level to store new information. Stack versus partial stack. So this is just introduction about what is the difference between these two scenarios. So as I said earlier, the stack cell is initiated so early, and it's a full stack version. So the cell cannot either go up or down the stack level, while in the partially stack memory cell, for instance, the cell can store at least the stack level, so can increase the level to some Q. For example, if we have a Q array level, then we have from 0 to Q minus 1 level. And just to mention here, if in the partial stack scenario, if the stack level equals 0, then it's a non-stack or healthy cell, because we can increase to any other array, the non-zero values Q array level. So this figure summarize the idea from the left. There's the normal cell can store any information, while in the stack add scenario, the classical stack add or the full stack we call it, we can store only the exact value on the memory. So for instance, we can store here, but cannot the other levels, or can add 1, but not up or down of this level. While for the partial stack, we can store the level or more. So at least the stack level. Our contribution, we have many code constructions for partially stacked memory cells, and we summarize in this extent abstract one of them when we have some U partial stacked memory cells up to N, and this is we have a theorem for this. We will explain it. So presenting code construction for mask and partial stack while additionally correct errors. So the main idea difference from Wachter-Zeh and Eitan Yakubi is that we can not only the partial stack, while we can do the error correction. Then we derived bounds on the cardinality and minimum distances. This is the deriving a sphere packing like bound. So it's based on sphere packing bound for any number of partial stack cells, and the generalization or generalizing the derived Gilbert-Varshamov like bound. So we present already in the ACCT Gilbert-Varshamov like bound for U less than Q, but in this new work we extended this, and we have now a generalization, and this is a new result we presented here only for this workshop. And this both of them for codes that can mask a certain number of partially stacked cell and correct error additionally. Then we have a numerical analysis, and this numerical analysis we compare how close our construction for any UR to sphere packing bound, and we check if our construction for any U partial stack cell less or equal and satisfy the Gilbert-Varshamov bound. So code construction over FAQ. This is our code construction one, and the theorem. So the main idea here, we have a generator matrix G that has a specific form, and this form, as you can see here, we have a parity check matrix H0 of a code C0, and this code C0 has enough minimum distance D0 that given here D0 greater or equal U minus Q plus 3. So this is the condition here, and it's not easy to find. It is not easy to find the matrix P, which is hard in general, but for instance, for example, we can start with any well-known code, a cyclic code, PCH code, or Hamming code, for instance, and then we can do echelon form, or we can do row operation and column permutation, and then we might get a specific form like this, but in general, it's hard to find. So this is the theorem, and then if we have this statement, so as a generated matrix for a code that has D, so G is a generator matrix for a code C, and it has at least D minimum distance, and this D greater or equal to T plus 1. So we can correct error with this code. And then based on the definition of algorithm 1 and 2 in the coming slides, this coding scheme is in construction 1 is a UT PCMC, so U partial stack memory cell and can correct T errors, while we consider here the stack level equal 1. Encoding and decoding theorem 1, algorithm 1. So here we can see we have an input message from a FAQ of length K1, and the stack position, partially stack positions with a stack level S equal 1, phi, and phi is a subset or equal from 0 to n. So we have we have n memory cell, and these some of these positions are partially stuck. So we find some vector called Z vector in FAQ, and this is explained in theorem 7. We will explain it here in Wachter-Zeh and Eitan, and we will also here repeat it, part of the proof, and compete then the code word C, which is the multiplication between M, the message, multiplied by the upper half of the generator matrix G, which is G1, plus this Z vector multiplied by H0, the parity check matrix from the generator matrix G as well, and this Z0 multiplied by H0 is the masking vector added to this M multiplied by G. We combine them, and this is a code word of the code C, and we can show this in our proof. So algorithm 1 finds Z, and then we follow from theorem 8 and 7 in Wachter-Zeh and Jacobi for the masking part, which just replaces the all-one vector with n-1k multiplied by n parity check matrix. And then instead of H in our theorem 1 here, or construction 1 here, we use H naught of the other dimension, which is n minus k 1 minus r, and this is the redundancy required for error correction part. This is the dimension of the H naught, so n minus k 1 minus r multiplied by n. This is the dimensions of H naught. The error correction part is related to nk code C1 and matrix G1. So here we need to choose R between 1 to n minus 1, such that the supercode C can correct T errors. And I explained this is not very easy to find. So R should be smallest value such that n minus R delta 1 Q code exists. Or here maybe we could say D1 exists. But because the notation here difference, because we assume we just try to find a good error. So P is hard to find in general. One way to construct P is to start with the generator matrix of well-known code, example a certain cyclic code and has a large enough minimum distance. Then we apply elementary or row operation and column permutation to have the desired form given in construction 1. And this is the decoding process. So we assume we received, we have Y, which is C plus E. So C is the valid output of algorithm 1 as a code word. And E is an error of Hamming weight at most T. So we can decode Y in C and then do the unmasking process because due to the so this is here written, the decoding and proof. So in masking process, due to the structure of matrix G, the leftmost significant position of C equals to the vector Z, and hence we can compute the message, the augmented message omega hat, which is M multiplied by G1. If we go back to this algorithm 2 here in the encoding process, as you can see this one, then and if you can see this here, so C minus this part, we have M multiplied by G1, which is omega hat, and then we can retain M. Now we have a sphere per compound on PCMC. This is a condition. This is the statement of the theorem. So we have two, we consider two scenarios for overlapping and non-overlapping. So in the overlapping, we mean error can happen in a different of the stack position. So we assume there is a stack positions phi, but the error happens in the rest of the n-u cells, the healthy cells. While in the overlapping, we consider that error could happen in all n, regardless or stack or non-stack cell. And this is the scenarios, or this is the inequalities here. We can prove it in the coming slide. So proof of theorem 2, non-overlapping. For any reliable memory cell, the cardinality M equal Q power K, these are equal Q power N. So we assume there is a healthy memory, so we can store N information on it. And this is the whole capacity of the memory, or whole the cardinality of the memory. While in theorem 2, in Ethan and Antonia, if we consider only PCMC, so they prove that the M with regard, there is a partially stuck memory cell is given by 3. So this is the inequality. So, and this is kind of easy to see this by for n minus u cells can store q levels, while the rest, from 1 to u cells, we can store just or can put information only on the level, at least the stack level. So from S up to Q minus 1, and this is here. So 3 give us the right-hand side of 1. So if we go back to 1 here, so this is the right-hand side. And since we are considering error correction capability, then this will for sure reduce the capability to store the whole Q levels, because this from in the healthy cells there is uncertainty from 0 to Q minus 1, and this is considered here. So follows from the Sperber compound exactly, but we have instead of the N, we have just N minus U healthy cells. And because we are in the non-overlapping scenario, so we just consider when this, what is the amount of information we can hear and what is the cardinality for which is here is given in this inequality. So the sphere of A of a radius atmos D is this, and then the total number of folds left-hand side of 1 is atmos the size of the whole space, the right-hand side. The proof of theorem 2, the overlapping. So similar proof for the right-hand side of 1 applies for 2, and error can happen either in the n minus u non-stack cell or in the u stack cell, such that we have the stack level plus the error at the stack position is or equal q minus 1. So we assume that, and then there are this amount of possibilities in 3. So this amount for the j erroneous positions. So then we have this another beta as a sphere, and now the calligraphic J denotes the set of the cardinality J minus J1 of the stack that is affected by the errors. So we assume not all the partial stack cells should be affected by that the additional error, for example. Then we have this amount as a most total number of possibilities, and the statement follows from the right-hand side of 2, as you can see here. So we have a bit different here because we consider error happens at the stack position. Analysis and comparisons for per compound on PCMC. So this is a graph shows you that we, if we can store all the information, because we have a healthy memory. So the yellow curve shows you that we can store the whole information. And then if we have a sphere per compound only, and we just considering the sphere per compound, then the red curve. While if we consider only PCMC from Ethan and Antonia's 2016 paper, we have the gray curve. And as you can see here, is just decreasing while the number of partially increase, because for sure that there is a least space between the stack level and the highest level, which is a Q minus 1. And we consider, for instance, here S equal 1. And if we consider in our case, the partial stack position and the overlapping case, for instance, and the non-overlapping case. So if the non-overlapping shown here in the blue, while the overlapping shown here in the black, This is another scenario. We just increase the number of T errors, and we see now the decrement in the line, because for instance, we have a lot of errors, then we have least places to be used for partially stuck scenario and to store this information above the stack level. Gilbert-Varshamov like bound on PCMC sufficient condition. Here we consider the Gilbert-Varshamov bound on PCMC. And this is a generalization of what we have done in the ACCT conference, which was for the only case when U less than Q. So now this is for any U up to N. And this is a statement of the theorem here. So we have this is 3 inequalities here, and we can prove this in the next slide. So first we use a probabilistic argument for the GV bound as in the Varshamov in 1957 to prove that the C0 dual of parameter and LD0 dual generated by a matrix H node of this dimension over FQ, whose dual code C node of minimum distance D node greater or equal U minus Q plus 3. And this is from our theorem, construction 1, theorem 1. So we need to prove these two events simultaneously exist. And this is why you use the Varshamov in 1957. Second, we need to show that we can extend the code C node dual to obtain a supercode limit C of a parameter NKD generated by a full rank matrix of larger dimension L plus 1, this or equal K, so that we apply the method given in Gilbert in 1952 with a suitable adaptation, which is a restriction version for linear codes from the suggested method in Gilbert in 1952, which was not only for the linear code, but for any code, to extend the code C node dual. Analysis and comparison, Gilbert-Varshamov like bound. So this is a new graph compared to the one given in the ACCT 2020 because it was for when it's U less than Q, while this one for any number of partial stack cell up to N. And as you can see here, our curve, the red curve, lies on the Gilbert-Varshamov bound. However, it starts at a certain point when this parameter D and K has a specific values, and we will have an error correction and masking code based on the probabilistic argument. And then for sure, when we extend it using the greedy approach given in Gilbert, we can have this graph, but started later from, as you can see here, at some point from K and D. And this is conclude our theorem here for the Gilbert-Varshamov bound. Summary, we proposed a code construction for combined masking and error correcting code for PCMC, deriving bounds on the cardinality and the minimum distance, necessary condition, a severe breaking bound for any U PCMC, sufficient condition, a Gilbert-Varshamov-like bound for any U PCMC, numerical analysis and comparison for severe breaking bound for any U PCMC and for Gilbert-Varshamov bound for any U PCMC. This concludes our work. Thank you for being in here, and I hope to see you in the workshop and answer your questions.